of dust that you're seeing here. They are working over there. So today we have Aurelio Carnero. He's from here, from La Laguna, Santa Cruz. Okay. He did a PhD in CMASS in Madrid, and then moved to Rio de Janeiro, to the Observatorio Nacional, where he's a postdoc, and he's been there for 2 years. He's deeply involved in the dark energy survey already for 7 years, and since 2 years also in SDSS, in the Sloan. So,
thank you for inviting me, and thank you for coming. Today's first day of work for many of, well, pretty much for everyone. And Happy New Year. Today I would like to talk about measuring galaxy clustering in photometric galaxy surveys. Basically, the first question that we should make is, what does cosmology study and why do we want to study cosmology? In this sense, when we study cosmology, we are focusing especially in the energy content of the universe and also in the dynamics of the universe. We want to know how was the past of our universe and the future. But in the process of knowing all these things, we also help in the knowledge of particle physics, astrophysics, even philosophy. Some concepts that arise in cosmology, finally they go to society and also influence in those other fields. Today, in cosmology, probably the main question would be if the universe is a lambda cold dark matter. This is the standard model today that we have, a universe made of almost a dark sector and the baryonic matter, which is almost like 5% of the universe. This model is quite well supported by many observations from the measurements of the isotropy and homogeneity of the universe, the existence of the CMB and its fluctuations, the light element abundance. All these observables point toward a lambda cold dark matter model for our universe. This model predicts that more than 90% is in the form of, is unknown yet, for the dark energy that was discovered in the 1988, or was confirmed finally with supernova, that it saw like the universe is accelerating in its expansion. The first idea, and the one that so far is valid, is the dark energy as a cosmological constant. But nonetheless, other possibilities that we have is like a new field, a new particle, modification of general relativity, or even that the cosmological principle is wrong, that idea that the universe is isotropy and homogeneous might explain the apparent acceleration of the universe. Also, there is another content in the universe that we don't know its nature yet, which is dark matter. In principle, most observations point toward a non-relativistic candidate that will come, and that's what people is looking for, extensions to the standard model of particles to explain for this dark matter. Cosmology actually has been like real science for the last 2 decades or more, with experiments, with CMB experiments and also galaxy surveys. With galaxy surveys, what we do is like an extensive survey of the sky in order to study the general properties of the cosmos, because we want to take as much area as possible. Nowadays, galaxy survey has become real international projects with many institutions that need to be collaborating towards the objective of the survey. This is what the DES collaboration is formed by universities from US, Brazil, Spain, Germany, and the UK. Galaxy surveys also are interesting in the sense that it's a multidisciplinary science. We need engineers, astronomers, astrophysics, and many other kind of work labors. The actual status of the galaxy surveys, the Slow and Digital Sky survey with the BOSS experiment is the most precise, it's probably one of the most productive scientific projects up to date, with hundreds of or thousands of publications and results. Today, last month they released the new results with the last data release 11. This is there's only one more release that will come next year, and then SLOAN 3 will close. Then will come SLOAN 4, and also DS that it's already taking data, PAU, GEPAS, and then other spectroscopical surveys at the end of the decade, like DESI, Euclid, and also LSST, which is photometric. In galaxy surveys, there are two distinct techniques that will depend on the design of the project, and it's all about how do we measure redshift of the galaxies. There are two distinct techniques. The first one is, by definition, the redshift is measured spectroscopically, but this technique is slow and time-consuming. So it was proposed that the resolution the resolution that you get in your results could be obtained also using an alternative technique, which is with lower resolutions, but that it will compensate the low resolution in the redshift with a much bigger volume and density of galaxies than the spectroscopic counterparts. In the photometric technique, we estimate the spectral energy distribution, taking images in different filters and reconstructing the spectral energy distribution. Some galaxies are better than others. In the case of photometric surveys, especially luminous red galaxies present a break at 4,000 angstrom. So this break can be detected as a function of redshift in different filters, and that will give you an idea of the redshift of the galaxy. Here I show an example of what happened to the distribution of galaxies for different cases. Here on the bottom panel, imagine that we are sitting here in the corner, down bottom left, and we look to the universe in real space. The distribution, would be the distribution of galaxies in real space. In redshift space, there are peculiar velocities of galaxies will introduce some variations in the redshift. So it's not exactly as the real space distribution. And then if we measure in these two panels above, shows two different examples of uncertainty in the photometric redshift. This panel represents the uncertainty in a survey like PAU or GEPAS, and on top is the uncertainty in the redshift given in dark energy survey. As you see, the information in the line of sight in photometric surveys is much poorer than in the spectroscopic counterpart. But nonetheless, it's compensated by the greater number of galaxies and the greater volume that we sample in photometric surveys. Galaxy surveys, one of the main questions that we want to look for is what's the nature of their energy and what's the amount of dark energy in the universe. So to study dark energy, the the main observables that we have studied dark energy. First, supernova Hubble diagram. It was how we confirm the existence of dark energy in the universe. Also, we have weak lensing tomography and galaxy cluster number counts, which are two techniques that are developing right now and potentially can give very good results on dark energy. I guess that weak lensing will be important probably for surveys of the next generation, although in dark energy survey we expect already to measure weak lensing tomography. We have also the study of galaxy clustering that we'll talk today a bit more. Also, we can study dark energy with weak lensing magnifications, Sunday, Seldovic effect, and other observables. I put here an intrinsic limitation that we have in cosmology, and it's cosmic variance. When we look to the universe, we only have one realization. We cannot repeat as many times as we want as they do in particle physics. So the significance is limited in cosmology by the idea that we have only one realization to look for. The galaxy clustering, basically what studies the evolution with time of the distribution of galaxies. In particular, there is a signature in the distribution of galaxies, which is the baryonic acoustic oscillation scale, which is a pretty linear process. That's why it's interesting to study, because in principle, the math behind and the systematics that applied on the baryonic acoustic oscillation are not many. In photometric galaxy surveys, when we study the distribution of galaxies, the main observable is the 2-point angular correlation function. Since we are losing the line of sight information, we can only study its angular properties. And it's defined as the probability excess of finding two galaxies at an angular separation with respect to a uniform distribution. So what are the baryonic acoustic oscillations in the primordial universe at the start of time? Matter and radiation are coupled. Matter include dark matter and baryonic matter. So baryonic matters are attracted in the overdensities, in the small fluctuations that exist in the dark matter field. But once the baryons are attracted, at the same time are repelled by the radiation pressure in the plasma, which form acoustic waves in the fluid. As any wave in a fluid, the speed of the perturbation is given by the sound speed. This sound speed is a function of cosmological parameters until, in the decoupling of matter radiation that we see in the CMB, this perturbation frees and the sound horizon scale becomes a standard ruler. It means that perturbation that exists in a distribution of matter will only grow because of the expansion of the universe. The baryonic acoustic oscillations are well detected in the CMB angular power spectrum, and it was known until 2002, or with the Sloan Digital Sky survey, that the BO signal was detected in the galaxy distribution. To study the galaxy distribution, we are looking at the power spectrum of galaxies, or the angle or the correlation function that are Fourier transform one of the other. The initial the power spectrum, the initial power spectrum, it's formed by the primordial index, a transfer function, which is a solution for the Boltzmann equation of all the processes that happen in that initial plasma. And then the evolution of the distribution, it's pretty much, with redshift, it's contained in the growth factor. The power spectrum depends in cosmological parameters. So what we want to do is to study from data, to extract the power spectrum, and in that sense we can fit our data and try to obtain the content of the universe. As I say, in photometric surveys, because we lose the line of sight information due to the poor resolution in redshift, we have to move to angular space, which is basically an integral on redshift of the correlation function, the spatial correlation function. These are some images of the encommoving coordinates of the power spectrum as a function of redshift, and also of the correlation function in configuration space. And the BO signal is a standard ruler. It means in commoving distance, it will stay at the same scale than in the same scale than we see at the CMB. Therefore, if we measure the BO at different redshift, we know the value of the acoustic scale from the CMB, and we can get information about the Hubble parameter. So far, I just present the formulas for the case of dark matter, but actually when we look to the galaxy distribution, we're actually looking baryonic matter. So we have to modify the power spectrum to include the effect of galaxies that are given by the galaxy bias parameter that in general depends on galaxy type, scale, redshift. Also we have another effect that it's an observable by itself, which is the redshift space distortion, that basically is a modification due to peculiar velocities within galaxy clusters that produce a distortion in the distribution of galaxies. It's also related to the growth factor with this beta factor. Also, there are effects of non-linearities. Before I said it's a pretty much linear process, but nonetheless, non-linearities affect the shape of the correlation function. We can see here in this plot the evolution of the angular correlation function at a fixed redshift of 0.4, and how the difference between linear and nonlinear theory affect the correlation function. There is another issue here, which is the projection effect, that, as you can see, it modifies the scale of the baryonic acoustic oscillation in the angular correlation function. This projection effect comes from from going from real space to angular space. This integral, in principle, is done in a redshift bin. So as the redshift bin is bigger, there is a damping of the BO peak in the angular correlation function. So basically, if we want to study this theory, the theoretical model that we base our measurements from the other side, we want to measure the distribution of galaxies. We want to obtain the angular correlation function from data. So in that sense, it's interesting to have a fixed, a clean galaxy sample, which give us a constant galaxy bias. This avoids us problem of maybe scale-dependent bias or other issues. Also, we need to know the selection function in the sense that we need to know how good the photometric redshift of our galaxy is. And then once we got our galaxy sample with an estimate of redshift and angles and position in the sky, we calculate the angular correlation function with different estimators. But basically, all the techniques consist in comparing the distribution of galaxies with a uniform random catalog. Also, I'm showing here how is the expression for the covariance matrix of this estimator. Here I'm showing some results that are actually with spectroscopic data. Actually, this is not photometric. I think photometric samples, we got the data release 8 of Sloan, but pretty much all the results that we got today with BO are from spectroscopic data. This is from Wiggle C with 5 sigma significance of the BO peak, and also we got the result from BOSS, and I think the significance of the detection is pretty good today, comparing with the significance that was detected the first time almost 10 years ago. So I have done like an introduction to the problem that we have of galaxy clustering, how to measure and how is the theory behind. And now I wanted to do like a summary of all the different steps that we need to do since we take data from the telescope till we go to the cosmological results. We take millions of images of the sky, and at the end we come with a number. How do we go from observations to cosmology? So first, we need a time-dedicated telescope. The galaxy surveys demand an intensive survey of the sky. Especially, also it's important that data is calibrated in the same system, and in that sense, you need time in telescopes. These are images of the Blanco telescope, which is the dark energy survey telescope, which is not, I think it's 50% of the time of the Blanco telescope will be dedicated to DAS for 5 years. Then we got the Apache Point, which is 100% dedicated to Sloan, and this is the Wiggle Z telescope in Australia. Also, when we do a galaxy survey, we need to define the objective, we need to design the technology, actually, the camera, and because the surveys demand a long time taking of data, we need to know what the objectives we want through all the years. We might want in the first years to cover the whole area, but going not too deep, or maybe we would be more interested in the first years going deep in some regions. Those issues should be defined by the collaboration previously to starting the survey. Also, the amount of data that galaxy surveys generates is quite big. For example, DS, it takes 400 images a night of 1 gigabyte. So this will be going for 5 years. Those data need to be reduced, remove instrumental signatures, also create coad catalogs of all these images, identify galaxies and stars. So it's important to have a good data management system in your collaboration in order to facilitate the work of the scientist, of cosmologists or astrophysicists. once the data has been reduced and has gone through data management and released for the collaboration, we need first to check the quality of the data, obviously. The quality of the data should be defined also previously to the survey with some science requirements. And in this step, we need to ensure that the quality meets the science requirement of the collaboration, looking at the astrometry, photometry. Those issues are generally looked by comparing with previous observations of standard stars, and we can look to the properties of your images. In photometric surveys, there's quite a big issue with the star galaxy classification. Spectroscopically, in a spectroscopic survey, it's much easier to check if your object is a star or a galaxy. But in photometry, it's not a simple task. A first order, the first thing that we can look to separate star from galaxies is the shape, or the spread of the magnitude. If it's round and it's a point, it's probably a star. So we can look in this. This is like data from the science verification data from DS, and this is kind of a first estimate of what are galaxies and what are stars. And it's important because the stars can deteriorate, can have a contribution in your measurements. So it's important to have under control, at least, if we cannot remove all the stars, to know the level of contamination. Also, as I previously said, to study galaxy clustering, it's good to have like a single galaxy population that will give us a constant bias. To do that, we need to study the different galaxy populations as a function of redshift in a photometric. Well, you need to consider that the different galaxy types, this is a color plot for different galaxy types as a function of redshift. Okay, this line goes here. So this is an example of what they have done in Sloan. They select the luminous red galaxies cutting in this area, which those luminous red galaxies were the one that at the start of the talk I said that have a clear break at 4,000 angstroms, which facilitate the determination of the redshift. This is probably the main issue in photometric surveys. It's how we measure the redshift. It will depend on galaxy types. Those that have clear signatures in the spectrum will be much easier to get. We will have a better redshift determination than those galaxies that might be flattened. So generally, even in photometric surveys, we will need at some point some spectroscopic sample in order to calibrate how well the photometric redshift behave. There are basically two distinct techniques. One is template fitting, where you compare your images, your values of magnitudes against templates of different galaxies. Probably those templates can be from previous spectroscopy surveys, can be a collection of those for different galaxy types, or it can be synthetic templates for the galaxies. And then we got learning techniques like neural networks. For the study of galaxy clustering, if we want to fit the full shape of the angular correlation function, the redshift, the uncertainty in the redshift will give you the selection function. This represents actually the real distribution of galaxies as a function of redshift. We study the angular correlation function in redshift bins. So in this case, it doesn't match the redshift limits. But just to show the example that we select galaxies from photometrically between redshift 0.5 and 0.6. But because of the uncertainty, this is the real distribution as a function of redshift of those galaxies selected in this redshift bin. Also, and quite important that we need to have well under control is the angular mask and the angular mask of our survey. This will provide us, we need to provide to the collaboration the information of survey depth as a function of sky position. As I said, the angular correlation function is obtained from data comparing the distribution of galaxies to a uniform random catalog sample. But this random sample uniform must follow the depth of the survey. Because imagine you got your galaxy distribution and you see a hole. Maybe that hole is real, there's no galaxy there, or maybe it's just because in that certain area you haven't observed properly, or maybe not as deep as in other areas. Also, in order to get to your results, you need to test all these issues of photo C, star-galaxy separation. So, because we've got only one experiment of the universe, what we can only do is reproduce in computers different realizations of what we expect is the universe we are seeing. Also, in order to study covariances between covariance matrix, it's also, there are two kinds of simulations. N-body simulation is a huge simulation in a big volume, and with time, you see how particles distribute, and it's quite time-consuming, but there are techniques that we can use, mathematical techniques, in order to create galaxy catalogs much faster that will represent the universe we are studying. That's, for example, in BOSS, they generate like 600 mocks of hundreds of thousands of galaxies in order to study the covariance matrix in the angular correlation function. And finally, we measure the angular correlation function. We got the theoretical model, and using typical mathematical procedures, we can get to the final result of our analysis, of our study. So basically, I tried to point some of the issues that are important in photometric surveys. And now to finish, I want to present an example of what we did last year with the photometric sample of BOSS, the DR8 sample. This is consists of 600,000 galaxies in that redshift range. We divided the sample in 4 redshift bins and measured the angular correlation function. Here on the right are the selection functions for all of these redshift bins. What is good in BOSS, they did first this photometric survey in order to select targets to do their spectroscopic survey. But what is good is they have a very well-known selection function. They know very well how the photometric redshift works for both. We did 3 distinct analyses. What we wanted to do with this work was basically to set like a, to look for the different observables that we will be looking later in DS, in a photometric survey. So we look for the redshift space distortion. To do that, we fix cosmology to a fiducial cosmology and look for this effect of the redshift space distortion. Also, we look for the BO position with an analytic approach. And this is like a novelty, well, kind of novel analysis that we did in the results of the CMASS sample, because previously only the BO, the angular correlation function was used only to look for the BO positions, but no one had done before a full shape analysis of the correlation function. So what we did was exactly, with this paper we saw that we were able to obtain cosmology with photometric data. So just to finish, I think it's a good time to study cosmology, lots of upcoming surveys, lots of public data already available for everyone. Those galaxy surveys, now they are kind of competing between photometric redshift versus spectroscopic redshifts, but both are complementary. Within galaxy surveys, one of the observables that will be used is galaxy clustering, that is good because it's kind of almost linear theory. And in the case of photometric surveys, those issues that are more worried are the redshift resolution and the star-galaxy separation. And yeah, also I present some results with data really say that it is the biggest photometric sample available today. That's it. Thank you.
Thank you very much. Questions?
I have one question about your paper. If you go back 3 slides, okay. So this is full shape analysis. How does compare with when you fit only for the position of the PAO?
That's interesting. I mean, I would like to study how maybe both observables can be put together, because when we did full shape analysis, if we free the equation of dark matter, equation of dark energy, basically we could not get much. We could not get constraints in dark energy. At this point, we only got constraints in dark matter and the galaxy bias. But as you can see in the marginalized matrix, for the full shape analysis, we didn't look for dark energy. Basically, we had no power to constrain. And with the BO, basically we didn't want to either extract to look for dark energy. It's true that we need to use the measurement in CMB, and the measurements from Bose or Wiggle set are much more precise at this redshift range. It was more like a trial of what we can do with DS, because here we are in the redshift range up to redshift 0.7. DS will go up to 1.4. So with that redshift span, then we will have constraints on dark energy. But with photometric surveys in this range that we have spectroscopic data, obviously the constraints in dark energy are still poor. No, the potential with the potential. The good thing about dark energy survey and those photometric surveys that will go to a redshift range much bigger. But in this case, we are still in the spectroscopic range. So,
and 2 slides before, the one before, yes, the red point is the value you obtained in the bottom panel for the bias?
That's a good question. What was the? I think that's a measurement done with a spectroscopy.
Your results are the black dots, right? Or?
Yeah.
More questions? No? Then let's thank Aurelio again.
Thank you.